Hey, this is Steven from RC Engineering, and welcome to the fourth week of February. So, obviously, in my development series, this is my development series. Obviously, in the fourth week of the development series, we do a rule of thumb series where we talk about a new concept and kind of explain on how we're going to use that to apply to better understand models and from those models understand the world to better so apply those to models to have fun, and then also those applied to the world, because generally what applies to models can apply to the world in some shape or form. So what I decided to do today is we're going to look at kinetics. Now there are two different types of physical, what we call in physics, right? And it's mechanical physics, classical mechanical physics. Is we have kinetics and kinematics. And as you see here, the two different explanations here on my screen. Kinetics is the description of motion with no regard to what is causing it. We're talking distance, position, angle, velocities, and acceleration. And kinetics are analysis of forces and torques that cause motion. Newton's second law. Equations of motion, sum of forces and moments, and it says work and energy methods, changes in speed, impulse and momentum, impact and collision. So those are what we're going to be talking about today. We're going to be talking about kinetics. Kinematics we might talk about later on, because I believe kinetics are more applied to what we're going to do in models, because generally they're easier to measure, especially in inside a vehicle, because all those are kinematics are mainly relative to something else, right? So how fast is it moving compared to the ground? How fast is it moving compared to air? How fast is it doing this? While generally the accelerations changing in rotation and stuff like that can be measured on the vehicle, on whatever model we're using. So that's what we're going to go into, and I'll talk a little bit more about that as we chase this rabbit down the rabbit hole. Okay, so number one, where did these classical physics come from? So one of the major players is Sir Isaac Newton. And Newton, as you know, sort of, and others discovered gravity and the, how to quantize that into data to predict how things will happen. And he had three laws. And laws are, again, I'm not talking about like governmental laws like in the United States or any sort of other developed country has. We're talking about laws of the universe. So basically what a law is something that was developed using the scientific method and then proven and was never able to be disproven. So it happens, as far as we know, it happens all the time and never does not happen. So these are governing laws. We call them governing laws of the universe. So gravitation pull exists everywhere, right? We've never found, there could be, but we've never found a place where that law is disproven. And once it's disproven, then obviously it is no longer a law. So that is these laws. So these are laws that Newton discovered and were never able to be disproven, thus they are true everywhere that we have checked, which is pretty much everywhere. Space, here on Earth, other planets, etc. So his first law, he developed three laws. First law, initial frame of reference, an object either remains at rest or continues to move at a constant velocity unless acted upon by a force. So basically what that means is if you have a car that's going forward and the car will continue going forward at that same exact speed until something else acts upon it to change speed, direction, up or down, so relative velocity, different directions, magnitude of velocity, which is speed, and then you have direction, which is the angle, right? So unless it's acted upon by what's called a force, it will stay at that speed going that exact same direction without changing. Second law. In another frame of reference, the vector sum of the forces, which are, again, vectors are magnitude. So for example, your speed, let's say 50 miles an hour, and then they have a direction, for example 3 degrees, or let's say west, or whatever. So we could say if your frame of reference is north, we're 3 degrees from north, right? So let's say let's say you had a compass on board, then that is a relative direction. And then you also have a direction in the 3D plane. So how are you going uphill, downhill, for example, stuff like that. So how is that relative? So for example, XY plane, flat plane, as compass, you're 3 degrees from north, and then let's say you're going upwards a hill at 3 degrees, right? So that would be a vector quantity where you have a magnitude, which is 50 miles an hour, 3 degrees from north, and 3 degrees up from sea level, from the horizon, right? Yeah. And then, so yeah, that's the vector sum of the forces, and we're going to go over forces right here. I also went over forces in another one of my rule of thumb series videos, is equal to the mass, m, which mass is basically weight divided by gravity. So it's basically content in your body. What does how much weight do those elements have in space, pretty much, where gravitation is low, because weight is your mass times gravity. So technically mass is weight divided by gravity, which is acceleration, which you'll see here in a second, of that object multiplied by the acceleration of the object, which is F equals ma. M is mass and A is acceleration. So what is acceleration as a quick recap? Acceleration is the rate of change of velocity of an object with respect to time. So for example, something that you would be very familiar with is acceleration of a car. So let's say you're going down, let's say you're going to race somebody at a stoplight. So when you stop at the stoplight and you're next to somebody you're going to race, you are not moving. So your velocity is, let's say your velocity with respect to the stoplight is 0 miles per hour because you're not moving. Then when you increase speed, let's say you increase to 5 miles an hour in 1 second, let's say, you are accelerating at 5 miles per hour per second. So basically it's the rate of change of your speed. So if you're accelerating, your speed is increasing every second, right, by the value of your acceleration. So what gravity is gravity is a constant acceleration towards the middle of the earth. So what you'll actually find is if you jumped up and down on a scale, that you would have a force. If you could measure force, your force would always be the same, right? Because your body's not changing. No matter how high you jump, you're inside, right? This is neglecting air resistance. Every time you hit the scale, you'll do the exact same force, because force is the acceleration of gravity, which generally we'll say does not change with respect to altitude, which it does. It does not change with respect to distance away from the earth. In actuality it does, but we'll neglect that. So it's constant, and it has to do with, again, distance away from the earth, and that's constant, and we have a measurement for that, which is 9.81 meters per second, or 32 feet per second. So that is a gravity. Now, so that's basically what acceleration is the rate of change of velocity. So how fast or slow are you changing your velocity? Also, it could be negative. Are you slowing down? Are you initially at 50 miles an hour going down the road, and next thing you know, a few seconds later, you're at 30 miles an hour, how much were you, in this case they say decelerating, which is a negative acceleration. Where'd it go? Okay. So force equals ma. So mass times your acceleration equals a force you put on the object. Third law, when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. Basically what that means, and I think they're missing some wording in there, if you have, for example, a wall or a floor or a building or let's say a car, I'll explain car in a second, but if you push you yourself, right, no assistant or anything like that, and you push on the side of your house, is the house going to move? No. So what you have, if you're sitting there leaning on the house and pushing on the house with your hands, you have what's called an equilibrium system, which means that both objects are not moving. You're not moving, and you're putting a lot of force on the building, and the building is also not moving. So both of you guys are not moving. So you're in an equilibrium system, or otherwise known as kind of steady, I guess you would say. But steady state. There's also something called steady state, but that's completely different. So it's an equilibrium system. You're not moving. The house is not moving. So according to this law, the house is not accelerating, and you're not accelerating, but you both have mass. So basically what you have is you have a sum right here, the vector sum of forces, and I'll show that right here by drawing it. So here is the house, and here you are, a little stick figure, and you're pushing on the house. Now you're putting a force this way, and the wall, in this case, what will happen, because both things are not moving, according to Newton's third law, the wall has to also be putting the same equal force back on you in order for it not to be moving. Now, let's say you're pushing on a car, right? Same thing, exact same thing here. So here's a car, right? Here's a car, and here you're pushing on it, right? Car's not going to move. Car's putting equal force back on you as you are back on it. As long as the car does not move and you do not move, they are putting the exact same force on you as you are upon it. Now, what if the car hits you? Let's just say, obviously pretty intense, but if the car hits you, then it's putting a way bigger force on it. And let's say you're trying to get it to stop. You're putting a way smaller force on it than the car is on you. Let's say even if you guys were running at the exact same speed. So let's say you're running at it at 15 mph, right? I can't really draw font in here, but let's say you guys are both going, this is going 15 miles an hour this way, this is going at 15 miles an hour this way. And let's say you're both going at, the acceleration is 1 meters per second, and you hit each other, the car is going to launch you because the car has a lot more mass. So even though you guys have the exact same acceleration, the car has, let's say, 10 times more mass than you do, let's say. It weighs 10 times more than you do. 10 to 15 times more than you do. So what it will do is it will take some of that force and give it to you and accelerate you back in the way that it's going. So the third law is only if you're pushing on an object and the object is not moving, right? And so what that says here is it says body exerts a force on a second body. The second body simultaneously exerts a force equal in magnitude but yet opposite in direction. And again, the opposite direction here. Opposite direction to what you're doing. Opposite direction to what you're doing. So, what does that have to do with models, and how can we use this to better understand models and the world that we live in? So, basically, what happens is you could use these ideas and these equations to really optimize your models, whether they're cars, planes, boats, helicopters, quadcopters, anything, rockets even. So what you have is you have the vector sum of forces. So what does that look like? Here's a plane, and we have plane and car example. Now, in the basic forces of flight, there are 4. And again, these are vector sums, just like you saw. So what we have here is we have lift. We have lift, which is up, thrust, which is this way, weight, which is down, and drag, which is backwards. So we have this fight between each of these particular pieces here, between these particular forces. These are each forces. You have a lift force, you have a weight force, you have a thrust force, and you have a drag force. So here you have lift, and then you have thrust, weight, drag. Now you could see here that we have a few things that need to happen in order for this machine to operate. So obviously, if you're trying to go this way, this is your desired direction, which is forward in comparison to the plane. Your thrust probably has to be greater than your drag. Because if your thrust is less than your drag, you're going to be going backwards, right? You're not going to be going to where you want to be going. So let's say you wanted to go from LA to San Francisco. If your thrust is going backwards, you're heading down to Mexico, right? Or San Diego or wherever. Another one is if your lift is less than your weight, you're falling out of the sky and you're hitting the ground and crashing into cars or light poles or houses and causing serious damage to yourself and others. So you need more thrust and more lift. So how do you do that? Well, when you design your aircraft, you run it through what's called CFD, which is computational fluid dynamics, which will basically tell you how much drag at a certain speed this plane is going to have. And by looking at that drag, you will be able to know that, okay, well, my propeller or jet or whatever, turbine or whatnot on my plane has to develop more force forward than the drag is coming back. So let's say in pound force, right? Because there's the pound force, which is a force measurement, and there's newtons, which is a force in the SI units. So pound force and newtons. Obviously 2 different unit systems. One uses kilograms, one uses pounds. So let's say that you're doing, this is just a random number, just kind of a smaller number, 10 pound force of drag. So obviously if I want to go forward, I need at least over 10 pounds of force. However, you can also have 10 pounds of drag and 10 pounds of force, thrust. 10 pounds of force and drag, 10 pounds of force and thrust. And what that means is if the thrust and the drag are the same exact size, it means that you're continuing forward or whichever direction you were going originally, but your velocity does not change. Because remember, force is equal to ma, and if force is 0, then that means that obviously your mass is not 0, so that means that your acceleration is 0. And what that means is it means your velocity is not changing. So you're not speeding up, you're not slowing down, you're continuously at this exact same rate, otherwise known as speed. So what you have in a plane is when you're flying in cruise, they call it cruise speed, your drag and your thrust are equal to each other. You're not speeding up, you're not slowing down, you're flying at a constant speed. So if you're developing a model aircraft or a full-size aircraft and you want it to cruise at 300 miles an hour, and you've already looked at the drag at that particular speed, you better be able to get a motor and a prop that will be able to develop at least the same force at that speed. So let's say you want to go 300 miles an hour. So, and let's say the drag at that speed using CFD over the plane is 10 pound force. Well, if you do want to indeed fly 300 miles an hour, you make sure that you have at least 10 pounds force thrust here. But if you were designing a race plane, right, and you wanted to compete in Red Bull, you want to make sure that you have way more power to drag ratio. So you want to make sure that you have way more thrust in the reserve to compete against that drag. And what that means, at any given speed, and what that means is you're able to accelerate and change directions very, very quickly. Another one is lift versus weight. So again, using computational fluid dynamics, you're able to measure the lift of your wing / airfoil, your horizontal stabilizer, and the body of your airplane. So with that, you will be able to know what is your maximum all-up weight of your model or your plane, which means fuel, pilot, electronics, cargo, everything. Basically, what are you taking off with? So if your plane only develops at cruise speed or even at takeoff speed, we're going to talk about takeoff speed, just getting off the ground. So if at your speed that you take off with, let's say 60, 70 miles an hour in a Cessna or whatever, if you're taking off at 70 miles an hour and you have, or let's say 100, it's probably more like 100, 110, somewhere around there. Let's say 110. If at 110 miles an hour, you're only generating, again, a very small number for just sample. Let's say you're only developing 10 pounds of lift. That means that you cannot be carrying 11 pounds. That's just not going to work. Because you're never going to get off the ground. You're going to run off a runway and hit a tree or fall off a cliff or whatever. So you want to make sure that your airplane is not loaded down more than it could actually get up off the ground. And especially on takeoff, because where it's not exactly the same as thrust as drag, is that if your thrust is equal to the drag, that's fine. You'll continue forward at the same velocity. But on takeoff, if your lift and your weight are the same exact force, you will not lift off because your velocity is not changing. You're still on the ground. So on takeoff, you must have drastically more lift than you do weight. And that's all in designing. And that's why it's very important here. Especially if you want to fly really fast, you want to have ample power to drag. Because as your speed increases generally, so you have what's called a coefficient of drag on this guy, which is basically a constant, which you'll find from CFDs, or if you're just doing general hand calculations, you'll find a drag coefficient, and then that drag coefficient increases with respect to speed. It's to the third power. It's cubed. So if you increase your speed 2 times, right? So let's say you go from 2 miles an hour to 4 miles an hour, right? That's 4, 16, 64. So now you increased it dramatically. So this is 32 times. You increased your drag 32 times. So your thrust must scale drastically compared to your drag. So also drag is in planes also very related to weight. But let's go to a simpler example, which is cars. So cars, you have your force forward. This guy really should have been first before the planes, but we can go back to the planes at the very end, go back to make sure you understand it, because I don't really want to start the video over again because we're already 24 minutes in. But anyways, So here's another example, is for automotive, whether it's models or full-size cars. You have two main forces, which is the three main forces. You have the force forward, which is of your engine developing power and then turning tires to make you go forward. Then you have the resistive forces, which are going backwards, which are wind resistance and friction from rolling, what's called rolling resistance, which is friction between the tire and the ground. So you have those two forces which are opposing your force that you're putting into it. So obviously, if you want to travel very, very fast in a high-speed car, you need a very drastic forward versus backwards drag. Oh, sorry. In this case, it's this way. Forward versus backward drag. So it's got to look like that. This size versus this size. And then eventually, what you'll have is you'll hit max speed of the vehicle, which is where, again, the forces are equaled out, which they're the exact same size at that point. So let's say that your engine could only develop this much power at a given RPM, at a given speed, let's say. This eventually, let's say you have a constant horsepower engine motor, which obviously, as you've seen from my very first rule of thumb series, that doesn't happen, because as the RPM changes, engines, whether they're electric or gas, change what type of power they output. But let's say, for argument's sake, that they are the exact same power, no matter what speed. Eventually, this drag, again, as velocity changes, it cubes how large your drag is. This guy will eventually come up and equal out to your forward force from your motor, and that will mean that you will cease to be accelerating, which means you have a constant velocity. So that is now your max speed. So as you can see, there's different things. Again, I probably should have done the car example before I did the airplane example. But I did simplify the airplane example quite a bit, and also this adds a nice little extra to it. If I would have really gone more deeply into the airplane one, probably would have lost you there. But anyways, so as you see here, very, very powerful to know kinematics, because a lot of these things are measured in the motors we get. Most motors you get are measured in forces, which is watts, which is force over time, right? Or which is power, which is work over time, and work is force times distance. So most of that stuff is measured in force. So the basics that you're going to do in planes, cars, boats, and stuff, if you want to go fast, is to maximize your force going forward and minimize your force going backward. And the more you could put going forward and the less you could put going backward, the faster your car, boat, airplane, rocket, whatever, will go before you reach max speed, where the drag against you in whatever medium that you're flying through, whether it's water or air or whatever, will equate to your speed going forward. And that means that you've hit maximum speed. So, for example, if I wanted to build this Trojan T-28 that's hanging here on the wall, I want to not change the streamline fit of the airplane as much, or streamline it even more. Put maybe some cowlings over the servos so that the air doesn't get caught in anywhere. Add a bigger spinner so that the air just kind of slips further over it, just to kind of minimize drag, but put a giant motor on it that gives me a lot of forward thrust. So I'm minimizing my drag and maximizing my forward thrust. That will lead me to a maximum, very high speed. And obviously, in this case, pick a right prop for that large motor. For a car, again, put a very large motor in it, and then streamline the body of the car, make it as minimalist and as streamlined as possible. And later on in this channel, we'll be going over CFD, computational fluid dynamics, which will take a 3D modeled car and we'll run some simulations of air going over it so we could see these forces of wind resistance, drag, lift, and all those other kinds of things. And also for cars, for boats, water resistance from the water flowing up against the boat itself. Alright, so that's been 30 minutes talking about kinematics. So I hope this explains a little bit more of what we're doing in the hobby of modeling. And also, engineers in pretty much every field are concerned with this. Whether you're, Tesla, Boeing, SpaceX, one of my buddies in CTO of Hoversurf building flying quadcopter motorcycles, even there, you need to know these kinematics in order to optimize things, to look at, battery life, maximize fuel efficiency, maximize high speeds, maximize control, maximize turning speeds, everything. Everything goes on kinematics or kinetics as far as classical mechanics. It's a very, very important concept to learn. In my mechanical engineering background at San Jose State, where I study, it's pretty much all we study is classical mechanics. And forces is very, 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 very important. Even more important than kinematics. But as far as what I think, but we'll go over that as well. So I hope you guys enjoyed this, and I hope that will spark you to look more into these topics. But these topics will be covered drastically on my channel because now we'll be using it quite a bit on other analysis videos and stuff like that, talking about forces and weight and stuff like that. Alright, so this has been Steven from RC Engineering. I hope you guys enjoyed this video. If you like this video, please subscribe for more videos like it. And if you would like to help me develop more videos, please head to my Patreon. Link is in the description. When you guys get there, you'll see some rewards to help back my channel, and also some other things like exclusive content to Patreon that will never find their way into my channel. Stuff like channel updates, what's going to be happening, and also me talking about specific, almost like podcast style, called Short Chat, where I talk about different topics in the engineering and the RC space that I don't want to take up time on YouTube. So some other cool, and then other videos like that I will never put on YouTube. But you'll find extra content there. Alright, so this has been Steven from RC Engineering. Thanks for watching, and I'll catch you guys later. Peace.